我刚刚吃完。
那就晚上早点睡啊，睡觉养病啊，睡觉养病啊。
which leads to the situation that the longer the cable, the higher the resistivity, for various reasons. The most simple explanation is to say, well, the increase in resistivity is proportional to the length of the wire, as a statement, which is underlined by empirical experiments, for example. The most simple explanation is to say, well, the results for those questions. Now we go into questions paper for resistivity, actually. And why is that like that?
Because P has twice the length. That means on top, they're the same material, so the resistivity. 那以后下次我还是要拿这种包。
下次还得重新交钱，就等于这次交钱拿这个。
啊？那不会把我的名字，就把我那个 position 换到下一个。
不会的。
啊？那下次还是抽签？
对，还是抽签。
那我这个就没有，为啥没有？
就现在不像疫情期间给那什么，给往后换，但是现在不给了。
为啥？
因为人太多了，就每次都10多万人抽签。
哇，怎么这么多人在跑？
因为疫情期间人们害怕，好多人就不敢跑，但现在已经不是疫情了，大家就愿意跑了。但是还可以用你前一年的成绩来参加，就报名的时候，哎，你这成绩挺好的，我觉得抽签可能对你，你看你这多好，10026，第一组的第26名，给你的名的什么很好，不像以前。
这个是不是叫
1043？
这个是不是叫？
什么？这是纸壳的呀？
是不是叫动签？
啊，那我放起来了。纸壳药。
我在上课。妈妈，我上课。
哇，你上课了？哎呦，我反正你吃完饭了。
What the hell happened over here? Oh. 3 weeks ago. Yeah, that's What?
Is the same. The so it, and also the diameter is 1/3.
So this is good.
What happened? Testing. Man, I'm bored. So bored, man. Oh my god, so boring, man. Are we gonna do the class or not, man? Oh my god. Hello?
Hello, Chris. Hi, how are you?
Well, yeah, I'm a bit sick today.
A bit sick, huh?
Yeah.
Sorry to hear that. Sore throat?
Well, it was mostly this morning, just like headache and just normal. I
Oh.
think it's a cold.
Yeah, probably, yeah. Yeah, then good sleep always helps for that one. And yeah, tea and vitamin C.
Yeah.
So, sure. Yep, hopefully it doesn't develop much further, right? Temperature? Already?
Well, it was slightly high this morning, afternoon, but right now I think I'm like maybe
Oh,
tomorrow
that's good.
morning I'll be completely recovered.
Oh, that's good, yeah, because typically you would even be higher in the evening, right? Which means if you were higher in the morning and now a bit less, that's a good sign, no doubt.
Yeah.
Okay, good. Okay, so then we said we continue still with them practical circuits. I think we probably deal with that last time today, I would say. And well, just to think ahead, what would be the next subject you like to work on, Chris? Do you have already some you should work on next time, for example?
I think we just follow the order.
Okay, all right, that's okay. So as I say, most likely we'll see, but for the practical circuits we have done quite some, but we will do more. The waves would be the next. I think that would be quite interesting actually, as a next subject. But again, we see. Huh? You can tell me then at the end of today if we still continue with circuits or if we already go ahead with the waves. Huh?
Yeah.
All right. Okay. Because we covered some of that somehow already. But I want to cover it a bit more accurately. But before we do that, I still want to we have a couple of questions to see which ones we do. And that would be just a sec. That was. Okay, my bad. Sorry. Okay, yeah, we can continue with this one, number 5. Last time we discussed. Nope, that was in the previous one. Okay. We have a wire, different materials, resistivities. Obviously, each section has a different resistivity, either single, double, or triple of the one of the others. There's a current. And now we would like to see how's the potential development along the lines, as we go along the wires. Sorry. So the question is it going down on a linear base? Is it kind of linear but in steps, kind of, or the opposite of this one, like still like that, but
wait, I can't see the screen.
Oh, we lost it again? Ah, sorry. Should have. Yep, no problem. Be here. Okay. Can you see it now, please?
Yeah.
Okay, all right. Okay, so I just go ahead once more quickly. So we have a wire, go from P to Q, 3 different sections from different material, and the resistivity goes from single to double to triple. So increased resistance, probably. And then you have a different pattern of how the potential difference will change as we go across. Will it be just a simple like that? Will it go like this, or will it go more like this? Or stuff like that? What would you say?
B.
B, okay. And why?
Because the first one is so its resistance is the lowest.
Okay.
So the potential difference, the decrease in potential difference is less, and then the second one doubles the resistance, so the change in potential energy should be double of the first one, and then the third one should be the triple of the first one.
Okay, yeah, good one. So clearly no such thing, right? Because that means it's flat, also the same along the wire, which cannot be. This one cannot be, because that would just mean it's one, but all along, so it goes down like that, just for one, with no different resistivity. Absolutely correct what you say. And this one, of course, is exactly what you explained, that's why it cannot be like this. It has to be along these lines. Huh? Okay. And again, we have a strain gauge, it's a length of wire with a uniform cross-sectional area. So we have a wire, its resistance is 2.5 kilo ohms, and strain gauge obviously is a type of measurement in order to see if there's an expansion in the pipe or not. So we see quite some practical applications, kind of. And how does that work?
So on the top, the resistance, so the length increased by 0.04, so top is times 1.04. And then the bottom is times 0.99 squared.
Okay.
And then the value that's calculated, just times it with 2.5, and I think that's the answer.
Okay. Okay. So just quickly. You said 2 point. How much did you say, Chris?
Wait, so 1.04 divided by a bracket of 0.99 squared.
Okay. Yep. Exactly. All right. Sorry. Okay. And then let me see. That's a bigger one. Okay, I think that's the last one. Then we go into the next one. So we have a thermistor, and the one is connected to the circuit as shown here. Huh? We have 9 volts of EMF, and the voltmeter, of course, has infinite resistance. So, and we now want to know the temperature of the thermistor, and the reading on the voltmeter is 4 volts. So how do we approach that question?
First, I think we find the ratio first. So on the 1.2K, it should be 5, and then so the ratio of resistance is 5 to 4.
Okay.
And to find the resistance of the thermistor, so it should be the total resistance in the the parallel part should be equal to 1.2K times wait. 4 over 5.
Okay. Okay, yep, 4 over 5.
And then we have so that resistance equals to bracket 1 over 1.6K plus 1 over X, and then bracket and inverse.
Okay.
And then when we have the resistance of the thermistor, we go to the graph.
Okay, yep. So what you said is, let me just write that down. So you said 4 over 5 times the 1200. Now, of course, and then on the other hand, we have then the. I just give you the value. Let's say 960. On the other hand, we have then, of course, the inverse of the resistors, 1 over R1, let's call it X, plus R2, 1 over R2. And on the other hand, which means we have this 1 over 960 is equal to 1 over 16, like you said, plus 1 over x or R2 or whatever. Huh? That means we have exactly then in the end 1 over R2 equals 1 over 2400. That is obviously 2.4 kilo ohm. Huh? Okay, so when we look at that, have it here, go straight all the way. Okay, that's a bit fat now. Oh. So we have to make sure it's on this one and all the way down here.
Is this supposed to be one line down from?
Yep. Oh.
Is it not? It's wait.
Yeah.
13 is supposed to be 13.
Yeah. I say. Let me see if I made my 2.4 correct. That's where we say we have 2.4 kilo ohms. That's a kilo ohm. I was too low. No, I was correct. 2.4. That's this one, huh? Yep.
But that's 2.5.
Yep. Is that okay? 2.4. Then go down here. Is that okay?
Huh?
Oh. So, no, okay. Go. Let's make it as big as possible. Okay. Then we'll go down to here, right? And then that must be, that's 15. So we go down to here. That would be 11, 12, 13, 14. So that seems to be 11.5 from what I see.
Huh.
So around, depends a bit on the accuracy, right? But we don't have 11.5, so
It should be.
So actually, when I look at it, to my opinion, because it's 2.4 kilo ohms, maybe I made a mistake. I know why. My bad. Sorry. Of course. This is 5. So this is one of those scales. Yep, I got tricked because it's not. It's 1, 2, 3, 4, 5. Unfortunately. So 1. So this is 5. My bad. Okay. No, that's I know. Okay, it just shows that we better count 1, 2, 3, 4, 5. Because to me that one looked a bit fatter, this one, than the others. So I thought this is 2.5. That's why. Okay, here we go. But I still end up on this one. 1, 2, 3, and it's 4. Okay, now we go. So here. But that's here.
13.
So that would be down here. So we have 11, 12, 13, 14, 15. Oh, I see.
4.5.
Okay. Okay, yeah, that's fine. So, but that makes 11. So we should have 11. Well, I think the graph is wrong, frankly speaking. Because if you have 2, that's fine. Well, things happen. I make it much finer. So if that's 1, 2, 3, 4, then we are here. But if we want to end up on 11, which is here, then you have to hit the graph here. So that means, because this is 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is equal, so 4 is here. It doesn't match, so the curve is at the wrong place for the answer, actually. So that doesn't. So what I want to tell you is, somehow something is not correct here, because if it's the answer is 11, that would be here. And 2.5 is here, right? So the curve would have to be something like this. I'll make it fatter. Oh, so it's not. So that's one of those unfortunate situations where the it's not completely correct. So that makes, of course, life very difficult for the student. There's no such answer as 11, unless the curve is corrected. Huh? Which makes you, of course, wonder if you calculated that correct, which you did. That's my point. And then the only way, then until I know, we know from the multiple choice it's 11, but there's, according to the curve existing, no 11. So in our case, it would be hitting it here. That's more like 12 and a half. So we would end up in, say, temperature is 12.5. Okay. So that's a bit unfortunate, huh? That the curve is not accurate for what the answer should be. Or that one has to be corrected. It has to be like, say, at least 12. Then we know, okay, that's the inaccuracy of our drawing, maybe somehow hitting the point. But it certainly is not that. Okay, Chris?
Yeah.
All right. Huh? Okay. And we move on. I can send you those additional questions then later on. Now, what I would like to cover is now more of this. And so internal resistance, that's something we have not covered really, because until now we always assume we have the exact voltage across its terminal. But as suggested by the EMF, but it's not. Several reasons. The supply may not be made to a high degree of precision. So we say it's like that, but in reality it is not like that, because the manufacturing was too, well, quality so-so, or the battery has become flat, etc. But what is more important is that in the end, all sources of EMF have an internal resistance. We always say no, right, to simplify the calculation. Now we want to look at the case and say, well, closer to reality is, of course, that it has an internal resistance, because the power supply is made of something as well. It's not one part, and that is the source of the energy, the EMF. It's made of wires as well, or of liquids, or of metals, stuff like that. So that, of course, has in its consequence a resistance as well. Hence, or we say the chemicals in the battery have on themselves have a resistance, or the wires, of course, have a certain resistance inside the battery, stuff like that. In other words, the voltage across the power supply decreases if it is required to supply more current. Or in other words, what we already know, but nevertheless to show quickly. So this is a very typical pattern. Where we have the current, we have the voltage, and what happens is that we have this behavior, of course. Something like that, let's say like this. So this is true as well. So the voltage across the terminal of the power supply increases as well, because yes, we have a theoretically stable voltage. We call the EMF, has 9 volt, 3 volt, whatever. But if it has to provide more current, it actually decreases as well due to the increased internal resistance. Huh? So, in other words, that's more of the natural behavior of an EMF. Instead of having a flat, straight voltage, it actually has a decreasing voltage as the current increases, or you may go the other way around and say, well, as the current decreases, actually the voltage noticeably. Sorry, goes back to where it was. It starts at a lower point. You may go backwards, for example, say, well, at a higher current, but if I reduce the current need, then the voltage will go up, actually. So the EMF becomes higher. That's just a phenomena which can be easily explained. Now, what we typically do is now to solve the problem is on one side then we take the battery, for example, or any source, but in this case the battery. So we have current, and of course we have, and then what we help ourselves with is to say, well, there's like a separate resistance or resistor as part of the EMF. Well, it's like two different elements that we say, well, this is the EMF with the potential, and this is the resistance, or actually I should make it a small r, that's more the convenient, a small r. But of course, that is more a model again, because in reality, of course, there's no separate resistor, right? It's just one, but it helps us to think a bit along the lines and say, well, actually, what we said so far, that the resistor has a straight, steady, constant EMF voltage is not the case. It has an additional resistance, and this is the way to indicate that a bit. And say this is basically like the internal resistance of a cell. And what we can do here is, of course, we say, well, complete it. Say, okay, let's complete the drawing. Of course, the circuit is only interesting if it has a resistor in it, at least. Otherwise, what's the point? The consumer or whatever. Sorry. It's a bit tricky. So, consumer and okay, so in that picture, now if we put aside the dotted line of the orange and look at that, then what are the two resistors, Chris? In what type of circuit?
The series circuit, there's the internal resistance and the resistance of the component.
Okay, and that would be like, if you look at these two resistors, how are they? What type of circuit? I mean, very straight, just one of the two choices. That's what I want to aim at.
In series?
Series, exactly, right? So we have the series circuits in that regards, helping our model to develop. And when we have, what is then the same across the resistors?
The current.
The current, huh? So we can actually say, if we go by our formula, I can say, okay, here we have the EMF, right? Then we have, of course, add them up, huh? Would that be correct?
Yeah.
So we can, because we say, well, actually, in other words, what we do is we add up the product of the current and the resistance, or in other words, we add up the voltage, right? So that's what you can say. So same thing. Now, I can as well say this. Why I say this is because how could I now go one step further? When I look at the resistor, what's the voltage of the resistor? Or the potential difference of the resistor here?
E minus I, the smaller r.
Okay. The when you have the external receipt, the external one, only that one. I know you already went one step further, which is fine, but I only want to look at this one first.
Oh, is it just the normal IR?
No, exactly right. So V equals IR. Exactly. So that means, or in other words, this one, I can write it as well like V plus IR. Huh? And hence it comes to what you just said, exactly. Then what is therefore my voltage in the resistance? When you look at the equation, forget about the one in between. Or if I say I want to know the voltage across the resistor, what will it be actually?
IR?
Yeah, on one side, but if I now look at the equation, taking into account the EMF.
EMF minus the internal resistance and the...
Exactly.
Right.
Okay, yep. So my voltage across the R becomes a V of the EMF minus the internal resistance. Huh? So that's where I see that actually that internal resistance, which I mentally separated, but of course which is ultimately part of the EMF, is reducing the voltage I have available here. Huh? Or quite often, we call that the terminal EMF instead of just the resistor. When we take into account the the resistance of the EMF, then we in tendency call that resistor here terminal potential difference instead of just potential difference. Huh? So I just write it down here once more. So we had E is I R plus R. On the other hand, V is R times I, and just make it like this, plus IR, V plus IR, hence my V is the potential difference minus the IR. Huh? Make that still do. So why do I choose the different colors? EMF is still the same, but now I include a certain internal resistance. This one, with the small r. Hence has the potential difference in the end, of course. There's a potential difference I have to deduct. And on the other hand, this one I rather call the terminal potential difference. Huh? Terminal in the sense of final, huh? Important to keep in mind. It's like when you have a terminal train station, means this is the end of the train station. It won't go further. That's the terminus. So it goes no further. So that means in that context it's not like a terminal like a keyboard or a terminal on electricity, whatever. It's at the end. So that's the one you can get, the final one, the ultimate one. That is the meaning of this terminal. Huh? Because you can't get more. So the EMF is nice to know, but in reality you will not get as much. That's what is so far always assumed, right? It will be minus with the internal resistance of the EMF, and that's why you only get the so-called terminal PD, or the max or the ultimate or the final one. Huh?
Yeah.
And under normal circumstances we don't consider that. But when it's specifically questions about that, of course we have to include it. And that's what we're going to do now in the next few questions actually, because there will be questions about that terminal one. And when we go into an example, here we have 0.4 amps. We have an EMF of 6 volts, and we have a resistor of 13.5 ohms. Now, what is the internal resistance of the cell? Or you may say the internal resistance of the EMF, but we usually rather than call it the internal resistance of the cell.
So times 0.4 times 0.4 times 13.5, and then 6 minus that.
Okay, yeah. 6 minus X or V, let's call it the terminal potential difference, let's call it the V, huh? Or is it the ion?
No, because I want to get the result first.
Okay, yep, alright, let's do that. So how much is that one?
5.
5, huh? Are you sure?
Yeah.
0.4 times 13.5?
Oh, 5.4.
5.4. Okay. So 5.4. So, I mean, now it becomes very fast, right? So, hence figures, we know that we have the EMF of 6.
0.6 is the potential difference of the internal resistance.
Okay, yep. X is 0.4 R, huh?
Yeah.
Like that? Answer, well, how is my R?
0.6 divided 1.5.
Okay. Oh, that's, of course, sorry about my handwriting, that's a bit bad. 1.5 ohms, huh? Exactly. Alright, good. So you see from that example, the internal resistance actually is, well, something, right, that my 6 is not really what I get. That's quite something comparatively, 1.5 compared to the 6 volt of the EMF. So obviously, in reality, when you have such circuits, it's not to be underestimated with the internal resistance. Huh? It's not just 1% or 2%, right? That's what I want to say. It's of a bigger magnitude. But for the sake of the step-by-step approach, we left that aside. Now we come a bit closer to reality. All right. Then the next one, that's this one, okay? So question A is to say, what is the current in each circuit?
So V over R, and total R is 4 plus 10 plus 10. 3 over 24.
Okay. All right. So I is 3 over. Okay. Did I forget something?
4.
Okay. Yep. Four. That equals
0.125.
125, huh? 125 amps, huh? Okay. What about, that was I or 2? What is 2?
Calculate the total resistance of the parallel
Sorry, for the second one. Sorry for the second one. Because I mean, it clearly plays with the idea of serial and parallel. So how does it look like for the parallel one? Because it gives us some information actually of the of practical consequences. So when we look at the same question, current, but in circuit 2. So for this one. Parallel.
I think there are two ways.
Okay.
I think the easier way is find the combined resistance first. So 1 over 10 plus 1 over 10, and then reverse, like inverse.
Okay, yeah, can do. That's fine.
So 5.
5 ohms, huh?
Yeah.
Okay. So I'll just write it down briefly nevertheless. Huh? So 1R, 1R1 plus 1R2. Answer 1. Well, that made it a bit. 5 ohms, huh? 5 ohms, okay. And now what about the next question? Or how to, well, or do you want to calculate 2 now? I mean, so what is the, well, either way, right? You can now look at question 2. So the question 2 is the potential. So the current is one thing, but in question B, we want to calculate the potential difference across the internal resistance. So we want to the potential.
For which current? For which circuit?
For both, actually, again.
First one is.
Oh, got that lost?
Huh? Wait, what? Huh?
Do you still have to? Do you still see the picture?
I only see the Skype screen.
Yeah, right. It's suddenly left. Yep, that's just it had a pop. It didn't show. It just left. So okay, no problem. Let's do that again. It's a bit unstable, unfortunately. Sorry about that. Okay. All right. Okay. So, okay again?
Yeah.
All right. Okay. So we also want to calculate the potential difference across the internal resistance.
So that would be the
terminal
current times the internal resistance.
Okay. So let's go with this one. IR, sorry. Also write it like this. IR, okay, yeah. How do we calculate that for the first one?
0.4 times the I forgot what's the
Yep.
0.125.
Yep. Okay. Don't have to write that one. Okay, that's 1 Carter. So how much would that be?
Uh, 2.05.
Yep, 0.5 volt, huh?
Wait, no. 0.05.
Okay. Question: is it 0.4, Chris?
Just 4.
Yeah, exactly. That's fine. Just that sometimes that stuff happens. So, okay, so of course then 0.5, no problem. Okay. So and what is that representing? That 0.5 volt.
The potential difference, that's the EMF that's lost.
Yeah. Okay. Yeah. Right. Yeah, exactly. Right. That's the one which is lost due to internal resistance, heat, most likely heat, usually, where we suffer with a less, potential difference than in the end across the circuit, right? Or the individual ones in consequence, of course, as well. Okay. And what happens now with the terminal potential difference?
The EMF minus.
Yep.
So 3 minus the 0.5.
Oops, sorry. 3 minus 0.5, obviously 3.5. That's now the terminal PD, yeah? So in other words, what does the 2.5 represent in other words? Instead of using the word terminal PD to explain to somebody in practical terms, what does that mean?
The potential difference that the components can get.
Well, exactly the max, right? They are not, even if the EMF says 3, the theoretically potential difference, now that's a bit too many potentials, but but in reality, or the actual and the theoretical, maybe better than potential again. So the theoretical potential difference and the practical potential difference, which we then call technically the terminal potential difference. Okay, good. What about, so that was cool. What about the second one? The second circuit in parallel?
We calculated that the combined resistance is 5. So 5 plus 4, 3 over 5 plus 4.
Okay. Okay, let me just, so you want to have, for the second circuit, right?
Yeah.
You have the 5 volts. But 5 ohms, I mean, excuse me. So we have 5 ohms for the total resistance. Okay. We have 5 ohms, yeah. And how do you, do you want to calculate the IR now? Because part R, so the current is, how much did you say? Sorry again.
5 plus 4.
Yep, okay, yep.
So 1 over 3.
1 over 3, amps. Okay. 0.33 amps. For A. And for B part, for the lost volts.
0.33 times 4.
Okay. Unfortunately, still, okay, I write it 0.33 because I always say don't mix, so better don't mix. Okay, so we get 1.33 volts, huh? And then what is the terminal PD in consequence?
So 3 minus that.
That would be, well, now we have to aim 1.67, huh? Okay, so let me put that in green. So here we have to, for the serial. So what can you kind of, I mean, when you look at that now a bit, we had the same values, right? EMF 3 volt, internal resistance 4 ohms, same thing for the second one. We just arranged those two 10 ohm resistors in a different way, serial or parallel. And now when you look at the result, same internal resistance for the EMF, huh? But the total terminal PD is different. Can you briefly elaborate a bit on that, Chris?
Because the first one is series.
Yep.
So the current is smaller, and so the effect of the internal resistance is less. But, actually, because it's a series circuit, so
Yep.
that the internal resistance and the resistance of the components they are in proportion.
Okay.
And the for parallel, because there's more current that's
Okay.
being drawn from the main loop, so
Yeah.
the effect of the internal resistance is greater because it has higher current and therefore PD.
Good. Very good. Yeah, I like your explanation. It's a good one. So that's something to keep in mind, right? So when you come from the other side and say, okay, what should I choose, serial or parallel, so to speak, because you have the same components, right? So it's like having a kit in front of you. Now what do? Do you do a serial or a parallel circuit? And depends on the outcome. Until now, we usually just have looked at the circuits and what do you calculate and what is the value according to this and that. Now this is a bit more going into the practical side, hence obviously the name of the chapter, practical circuits, because you want to influence of what you get, and what you want to get is based upon, of course, what you are designing. Is it about the current which should flow higher? Based upon exactly the same. So the magic insofar is by arranging that a bit differently, you can get a higher current compared to the other one. But of course you pay for it, right? Insofar, on the other hand, with the terminal, the PD you can gain across, or maybe you want to have a higher terminal potential difference, as a terminal potential difference, hence you rearrange it differently. Huh? Okay, good. So going into that one, and let me just go first a bit into that one. 6. Yeah, maybe we do that one before. Let me see. It's a practical, a comparatively practical one. So that we say car battery. It's about the car battery. Car battery. But for a standard car, huh? So not an electric vehicle, that would be a different story. Car battery has an EMF of 12 volts. That's very common, maybe 24, and has an internal resistance of 0.04 ohms. Seems very small, huh? And the motor draws a current when it starts of 100 amps. Huh? So in other words, for the normal combustion car, why do we even need a battery, Chris?
to store energy.
Of course, you're right, per se. Battery, we want to have energy, but we don't to have energy available. Put it like that. I wouldn't say to store energy per se. It's more like to have stored energy available. And for what purpose do we want to have that stored energy available? In a normal car, a combustion engine, not an electric vehicle.
For the like the air conditioning and the other functions.
Okay, yeah, true. But if you, sorry, I don't laugh about you. It's fine because, yeah, that's a typical situation in, let's say, age. Huh? Air conditioners, maybe 20 years ago or 25 years ago, were really not common, but you still needed a battery. So why would you, even without any electric, say you have manual windows to go roll up and down, you don't have an air conditioner, you have a very simple car, or maybe like 100 years ago probably, and you still need a battery. Or do you remember, let me ask you, still the same question but from a different angle, have you seen maybe very old movies where they had to go in front of the car and they turned something? Have you ever seen that in a movie? More in a funny movie nowadays, usually. The driver is not yet in the car, so he has the brake on, but he goes in front of the car and takes kind of an tool in order to turn. The point is, cut the long story short, you need to have the combustion process inside the engine to start.
Oh.
That the point is when you have, or of course nowadays we don't see so many diesel taxis are gone. The diesel taxis are gone anyway. But in the past, the taxis in Hong Kong were all diesel engines. The difference between the diesel engine, which is actually again named after a person, Mr. Diesel. He was really existing and not the jeans, but from before, a German. Same as for quite often the combustion engine is called Otto. I mean, nowadays we don't hear that so often anymore, but that is Otto and Diesel. Diesel was the name of the one who used what we call diesel engine, diesel gas, and Otto is what they have, the gasoline. So that's the gasoline. He was called Mr. Otto. So we have quite often it was referred to as an Otto engine, what we call a combustion engine. Now both are combustion engine, but the difference is that this one is self and this one needs an initial. That is self-combusting. So if you compress, which we are not, that is thermodynamics, but if you compress that diesel fluid, which is type of a gas, but gasoline, but we don't want to name it gasoline in this context, petrol, right? Quite often we call this one petrol, and this we call this diesel. But both is gasoline, a gas station, or also it's more in a liquid form than in a fluid form. So this is self-combustion, and the other one is initial. So what you need here is a spark. You really like a match, which same thing. If you have gas, as a petrol, it has fumes, hence it's comparatively dangerous. So if you have a cigarette just glowing, not even an open naked fire, and it's too close to the gas tank, of course, and you open it and the gas fumes come out, they explode. That's exactly what happens inside the combustion engine, right? But in a controlled way, of course. So you have this metal cylinder. That's why we quite often say, is it a 1, 2, 3 or 4 cylinder engine, or 5, 6, 8 cylinder engine? In what way? Maybe V12, not going into that. So that cylinder is like, of course, metal, block, outside, inside, and it has now some gas, or lean, petrol. And you squeeze it, that's thermodynamics, where you have P, V, R, T, and you start to squeeze it down. So you squeeze it down and down and down. Now when you do that with the diesel, due to the temperature increase, because volume increases, pressure increases, hence the temperature goes up, and if it reaches the critical temperature, it will self-combust. So it will inflate, it will explode. That's what diesel does. The petrol you can squeeze as long as you want. It will not initiate the spark. It will not explode. That's quite interesting to know, because the point is very high of self combustion. So that's why you need a spark, and the spark is delivered from the outside with the petrol. Huh? And that is a pretty high voltage actually. And that spark ignites gas, a very highly compressed gas. Of course, the gas then expands and pushes the combustion, that one, up again. And henceforth you have the motor running. But you need so you need the car battery basically only to provide the current for the spark in order to initiate and make the gasoline explode in the chamber. That's why you have a battery first of all in the car. Is that okay, Chris?
Yeah.
So, other than that, you would not need. That's why a diesel engine has no battery, first of all, because you don't need it. It is self-inflating, ultimately inflating, self-firing up itself. So, coming back now to circuits again. Question 1 in that context is, what is the terminal PD? Huh?
Just 100 times 0.05.
Okay. That's part of it, the terminal PD. But how do you calculate it? Something was missing, what is it?
12 minus 100 times 0.04.
Exactly, huh? Alright, yep. So 12 minus 100 times 0.04, huh? 0.04. And that is 12 minus, how much is that? 100 times 0.04.
Just 4.
4, huh? Okay, yep. 4 volts, huh? So, you get actually only 8 volts, huh? So that's actually now quite massive when you think about it. Well, you have a 12 volt battery, but you need, of course, like you said it before in the other, it's 100 amps is a very high current. That is actually quite something when you think about it. That you need 100 amps to start the engine. The cylinder is comparatively small, right? Maybe 600 cubic centimeter or less actually. And then it's compressed, so it's even less, but there's the gas inside. Yet it needs 100 amp current in order to ignite that. So that means obviously you need to have a pretty high voltage ultimately inside to get that. So you lose a lot, huh? That's the point. Even with a very small resistance, you use a lot because, of course, you have a high current. Hence, even the small resistance leads to a high loss or lost voltage. Huh? Okay. Then question B. Of course, now goes further, like what you said. That was to start. Now, when you look at the headlamps, not LED. That's another reason why we nowadays have always LED or LCD actually light. The headlamp says 12 volt, 12 volt, 12 volt, 36 watts. Now what is the resistance of the headlamp?
Find the current first by doing 36 over 12.
Okay.
And then times 12. Oh, no. 12 over current is the resistance.
Okay. So Do you um is there is maybe something missing? How come? What is the power, Chris? Because we have the power, right? 36 watts. How do you calculate the power?
Volt times amps.
Okay. And but you want to know the resistance. So how's the link there?
We can find the current and then use the voltage and current for the resistance.
Okay, so the current we have, right? That's 100 amps.
Oh.
So, right, there's something missing, right? Because you want to know the R. So how do we bring the R into the equation? Or the resistance? Because right now we say, there's an easy way, kind of, to say, okay, power is voltage times current, and there's a second formula, actually. Do you remember that one? To calculate power?
And 4 times velocity.
No, not in that just really in the electric content. It's good what you say, but purely in the context of electricity now. There's a second equation we can utilize. Because if you don't have, depends on either you have something or you need to calculate something. Now we need to calculate the resistance. So far, we only have P, we have P, we have voltage, we have current, but there's no R. So it's like, okay, I can't calculate what I need to know, right? So what is the second formula for power? It must contain
I squared R.
Exactly, no? V squared over R, huh? Correct?
Yeah.
Okay, so what you could do is just say, well, V is IR, right? Hence, of course, then you rearrange it in this case and come up with exactly this one. So if you put that one into this one, you get that one, huh? Because I would be V over R, huh? Okay, so either you can deduce it by always using that one, always helps a great deal, always, it's always correct, or you just remember it. That's my point, huh? And always look at what you know and what you don't know, I mean in terms of what values are given, which values are not given, or which parameter do you have to calculate. And now clearly, now we have found the one, because we need to know R, huh? Hence, what is now my resistance, Chris?
Equals 12 squared over 36.
Great. Okay, that would be what? 12 squared is how much?
144.
Yep. So we get, of course, a very nice relationship. What is the resulting resistance?
4.
4 ohms, huh? So 4 times 36. All right, okay. Well, so the resistance of a headlamp is 4 ohms. Of course, we're obviously going at something. Because when what will be the power output? So that's what we calculate now, huh? So far, or in other words, right now we have not included the I. That's the critical part, right? That's part of the question actually. So we have calculated it with the resistance as given with the value. Well, the headlamp has 36 watts. What of course is not said now is when the car starter is not in operation. That's what is not explicitly said, because when the headlamp is 12 volt and 36 watts, that means okay, like what we just calculated. It has 36 watts. The voltage is 12 volt, right? That's what we take. 12 volt, the EMF at full power, and we have calculated the resistance of the headlamp based upon its 12 volt and 36. But now if you go one step further and want to calculate the power output, we can just put it on this side. When it's in operation, then how can I calculate now the power output of the headlamp when the starter is in operation? That means the moment I start the engine of the car, and the battery has to provide the 100 amps. What is then the power of the headlamp?
I don't know, to maybe consider I think we consider the terminal voltage.
Yeah, very good. Exactly. Absolutely. That's a smart move. Because now we could make life complicated, but actually what we would do is we would start it all over again in terms of calculation and come up with the same result, right? Because you would have to include now the resistance of the EMF. But we have done it already. Of course, that was now a bit on purpose, at least not from my side, but could have been, in terms of thinking about, hey, I can actually, of course, use exactly the same formula, but I will change the color. So this is still the resistance, but I make it in blue. But this one is now, that's why, this one is now the red one. This is my terminal PD now, exactly. Because it's in operation, so the EMF is accordingly reduced, because it has to provide 100 amps at that very moment, and henceforth I can use the terminal PD, exactly. Taking into consideration, of course, the resistance at that very moment when it has to provide that 100 amps.
So when we calculate only the headlamp power, when we are given only the headlamp power, does that mean the current is small enough that we don't have to consider the terminal?
It's a good consideration. Yeah, it's a good consideration that we. Yes, that's what it is. What it implicitly contains. Then otherwise it would become too complicated. Or we could just have another sub question and think about what situation are we dealing with, right? Correct. Yeah, it's correct what you say. So that's why we say now, this time we say 8 square divided by 4, and henceforth no, wait. And the EMF, or now what? Let me see if they really phrased the question properly. No, each headlamp still the same. They make it now a bit complicated, I think. So the R okay, so which R would you take now, Chris? So sorry, I have to.
Four.
Yeah, exactly. Huh? Okay. So we got by 4, and we do this one by 8. Huh? So what value do we get?
16.
16. Huh? So 16 watt. So before we had 36 watt for each headlamp on their own without the startup situation. When it starts, it only provides 16 watts. Of course, the smart way is actually, because we could go the other way around as well and say, what does it really mean for the car to start? To switch off the headlamps and then start the car, right? Because then there's more power or electricity current in that case available at that very moment as well. But that's now going too far, huh? Because we are just looking at what we just discussed. Huh? Okay, so but important is you see when we look at the two different scenarios, this one was from the terminal PD. I should have not done that in red, actually. Sorry. So to make it with the sorry, I don't want to make that red because here that's the one we want to know, but otherwise we just make it blue. So the R we want to know, make it that one, so that's better. Sorry, just a bit for the clarity of the. And this one is this one, and hence we have it in 4. Make it this and make it that. Alright, yeah, I think that's more clear now. So what we talk about is now we have the headlamp which has 4 ohms. And in subsequence of that, we only want to calculate what happens when the headlamps are on. So we need to calculate theirs and have it, of course, with the voltage, which is only the terminal one. Huh? Okay. Then that's the one I want to do next with the potential divider now. That would be this one. So something different. Now that was the terminal potential difference. Huh? Now the other one we discussed that before in all the questions is to have a potential divider. And we have basically 2 circuits here, right? You can see that A and B. We have 2 resistors, R1 and R2. Here, separate. And what we have here is we have a so-called variable resistor. That is what we show here. And this is indicated with this one. So these are fixed points. Of course, we just measure the voltage, for example, the potential difference according to that resistance. Whereas this one is variable. That's indicated with that arrow. So I can slide it up and down. Huh? So that means I change my resistance as I slide up and down. Hence the potential divider. Because the potential in consequence will change. Is that so far obvious, Chris?
Yeah.
So we are not going to spend the time on really going to the, let's say, derivate how the potential divider equation originates. What we are interested in simply in say, okay, how can we link the voltage output, meaning as a result of that variable, the division of how I split the resistance. Is it a one-on-one relationship, or is it a most 9 to 10 and 1 to 9, 1 to 8, whatever. So that has a big impact on how I make the resistance here accordingly for the voltage. So in other words, my voltage out is depending on, of course, the ratio of R2 of R1 and R2 times, of course, the voltage in. That's okay. See, it seems quite logic somehow that we say, okay, the ratio of what is included here in the bigger is depend. In other words, the sum of them, of course, R1 and R2 together. And how does that work if just R2, the one providing the potential when I'm interested in this section here? Pretty obvious. Now, if I want to calculate now the output voltage, so what would that be now in my second situation? Of course, if I take it 200 and 200, that's pretty obvious. But if I now look it into a potential divider, then what would I get? Let's see. So voltage out now, R2, let's take it as 200. And now we have 400, because R1 and R2, times the voltage in, times 6 volts. So what do I get, Chris?
3.
3, huh? So obviously no difference to what we had before, because it's a split of 50-50 between the two. So 202, or each are the equal value. Let's put it like that. They both have the same value, so 200, 200. But of course, if I start to change, it's a different story. Huh? That's where it comes all out. So if I would now assume I want to achieve a certain result, that's when it comes into play. Huh? So, and how to do that? That is when they play around, so to speak, with the resistance. So from its full range of the resistor, and I go here to the next one, this one. So this is a very typical one, so that indicates my variable resistor, and hence I need to know what is the range. So let's say R2, I can as well call that one R1, doesn't need to. And my R2 range has a resistance from 0 ohm, that's the beauty, to 40 ohms. Huh? So that's more where I look at the ohms of it in order to get the voltage out. Now, how do I, and I want to calculate the range of V out. Huh? So obviously this one. So how do I determine the range?
The range is
where do I start with, Chris?
0.
0, okay. So 0 ohm. What
And
is
then
my voltage out?
the largest one is 1/5 because total is 50 and no 4/5 because it's 40 ohm
Okay,
times
so
10.
okay. So you say the R2 has 0 ohm, huh?
Yeah.
So 0 resistance. So what is the voltage out I get?
Just 0.
Exactly. All right. Okay. The V out. What if I go to the max?
So 4/5 times 10.
Okay. That means
So 8.
8 volt. Huh? Exactly. Oh. So that's there you see. It's very straightforward, but still we have to wrap around our head a bit what it really means with that variable resistor. So I can control now. That is exactly what I actually want, because I want to have a range from 0 to a certain value, 0 volt to 8 volt, with which I can then achieve certain results, of course, right? Based upon how I set the resistor in this variable situation. Okay. So this is for the potential dividers. Well, we can just quickly cover that because we've already more or less discussed that for the sensors. And of course, why we deal with the variable resistor first is because, of course, if you have the sensors, you have nothing else but variable resistors. So when we talk about the light, also the light resistor, the light dependent resistor, the LDR, then of course we have basically more or less the same set. It's just that this one is exactly delivering us different voltages, huh? Based upon the different resistance. And that is obviously dependent on the light. So what we can see here is if you look at this one, the LDR, what can you say for that one? What happens with the resistance?
Increasing light intensity is decreasing the resistance, but the more it decreases, the less faster it decreases.
Okay, that's one thing. It's not linear. Yeah. Okay. Yeah. It's exponential, non-linear. It's exponential drop. And what does that mean for my circuit? When I for this light sensitive resistor? What am I interested in here? Or how does the voltage change? That's probably the best question.
Higher light intensity would have lower potential difference.
Okay, yep. So we have to drop in voltage, exactly. And what does that mean in consequence when the voltage drops, probably? Or maybe go the other way around, maybe. So basically, when the light intensity decreases,
But it increases the potential difference.
okay,
And so other
And what-
components have less potential difference.
okay, and henceforth, when you think of the current,
Decrease.
right, okay. So, and then you have the same setup, but with a thermistor, with a thermal resistor. So let's say a metal wire and the thermistor. So the metal wire is here as a comparison, but the thermistor is like that. So let's start with the metal wire. What is the behavior of the metal wire?
It has a steady. It obeys the Ohm law.
Yeah, okay. But
So it,
what happens when the temperature increases? What you see here?
it the resistance also increases.
Yeah, exactly right. So that is so it will probably so. In other words, it will it if it would follow Ohm's law, it would stay like that, right? Because I mean, in this context, we don't know about the I, right? But if you think about the typical resistance current diagram, then we have a certain situation of what happens with the resistance. So we have either, depending what is what, it looks like that. But as the resistance increases due to the temperature, not to the I, for the same point, right, at some point it will start to change its behavior. So it will become non-ohmic. Huh? It's like with the lamp. If the filament lamp starts to heat up, temperature goes up, the resistance goes up, so it will be less light because less current coming through. Remember that, Chris?
Yeah.
So so what we are interested here is just because this one, it's just in reference to the thermistor, but the thermistor has a total different behavior. So the metal wire is not constant because it will increase its resistance due to more chaotic movements, let's call it, of the electrons. And of course, the starting movement of the grid as well, especially in the metal. So the electrons will bump more often into the protons, basically into the solid grid, as the solid grid is not that solid anymore, and hence overall it will have more movement. And more movement means higher temperature, means more resistance, because the electrons can't flow so smoothly anymore under potential difference as before. Hence the resistance goes up, which means that the current will drop.
The thermistor, because the thermistor,
say again, sorry?
the thermistor, because it needs energy for the electrons to be released. So without the temperature, it will have high resistance.
Okay, yep, yeah, exactly. Yeah, good one. And henceforth, of course, the opposite is true. When it's at a high temperature, then of course the resistance will drop. They can move freely. Huh? So that's in temperature different behavior, right? To what we see from the metal wire. Huh? So this one is not quite steady. It will actually increase slightly. Right? That's the point. But this one will go from extreme high resistance. I mean, if you take the same temperature point, room temperature, then this one has maybe 100, and this one is 10 times more. Huh? That's what we want for whatever reason. But when it increases in temperature, the resistance goes down. So when the resistance goes down, what may happen? Or why would I want to have a thermistor in place?
Higher temperature will allow more current.
Okay. And that means that's, let's say, good for an alarm, right? So it may need a certain or voltage. It depends on how you design it, so that the alarm goes off because the temperature increases. Huh? Okay. All right. So now for next time, Chris, would you like to continue with some more exercises in terms of these circuits, or would you want to move on to the waves?
Maybe you could send me the questions and then we move on to the waves.
Okay, can do. Yeah, I do that. Huh? Okay. Then we move on to the waves. I send you a paper and some more and some questions. Huh? Okay.
Yeah.
Wow. Okay. Then see you next Friday.
Yeah.
And
See you.
recovery next time. Huh? Have a good week.
Yeah. You too.
Thank you.
Whew.